So our next talk is going to be by Guido Roberts-Borsani. So Guido, if you want to get your slides set up.
Yeah, sure. Let me see if I can get this right. If I do that, can you see the slides?
Yeah, that looks good.
Is that the main one or is that the presenter view?
That's the main one.
Okay, great. Yeah, I'm good to go whenever suits.
Yeah, okay. Thanks, Guido.
Okay, so hello everybody. My name is Guido Roberts-Borsani. I'm a postdoc at UCLA, working in the group of Tommaso Treu on especially high redshift galaxies with HST, ground-based spectroscopy with Keck, and also preparing for Tommaso's JWST ERS program. I'd like to thank, first of all, the organizers for giving me the opportunity to talk today. My talk today is going to be on one of the largest searches to date for luminous redshift greater than 8 galaxies with HST using pure parallel observations. The paper has recently been posted to the archive. I've also posted it onto the Slack channel. So if you're at all interested, please feel free to have a look. So why are we interested in redshift greater than 8 galaxies, and in particular luminous galaxies? Well, the study of high redshift allows us to characterize the last phase transition of the universe and try and understand why it went from a neutral state to an ionized state. And bright galaxies form a crucial component for regulating the overall shape of the UV luminosity function. So they are especially valuable. These are some of the highest redshift confirmed sources that we know of at redshift greater than 8. They're especially rare, and you need especially large volumes to try and search for them. So these luminous galaxies are, very, very valuable, and they also form ideal targets for follow-up spectroscopy. However, there's a little bit of a caveat, and most large and deep surveys that try to look for these bright, high redshift galaxies typically make use of single pointing observations, which can be affected and plagued by cosmic variance effects. So you don't know whether these regions are representative or whether they might be characterizing particular underdensities or overdensities. And this is kind of highlighted by this nice plot by Brant Robertson, where you see various survey sizes in a cosmologically simulated volume at redshift 7 or so. And if you pick this particular region over here, you can see this sort of good simulated region. If you place it in one part of the simulation, you might see an overdensity, but if you place it in another, you might see an underdensity. And so you don't really know whether these pointings are representative or not. And for comparison, that's what one HST pointing looks like. So in this talk, partially introducing the Superborg Survey. This is a compilation of extragalactic HST with C3 pure parallel surveys, where the imaging has been homogeneously reduced with a new and improved pipeline. This compilation of data sets includes all of the Borg cycles, Hippies, COS, GTO, Clash, and relics as well. And this gives then a total of 316 independent sightlines, which have been consistently reduced. This is shown in the top part of the plot on the right. This is from Morishita, 2021. Takahiro Morishita is the one who compiled this data set and reduced it. So I encourage you to go look at his paper if you're interested. And the plot at the bottom here on the right shows the typical 5 sigma limiting magnitude. So you can see for H-band, this is for H-band, we go down to 26.5 roughly, and even lower down to 27 for some fields. So we use a subset of this data set to search for redshift greater than 8 galaxies. In total, the combined data set affords 288 independent fields, or roughly 0.35 square degrees, or if you want it in other units, close to 1300 arcminutes squared. The plot on the left compares this to other HST surveys that have been used to date, and this is one of the largest ones. It's about 1.4 times larger than the combined CANDELS plus ERS fields. And on the right, you can see the different bands that we have available to us over the at least 75% of those 288 fields. And so you can see these are all, this is all deep imaging in the near infrared, crucially with these Y-band filters and J-band filters needed to characterize galaxies at redshifts greater than 8, as well as optical filters to ensure that you have non-detections blueward of the Lyman break and ensure that these are truly high redshift galaxies. We also have Spitzer IRAC imaging over roughly 50% of the data sets, and this goes a long way towards ensuring that these aren't low redshift interlopers. So we apply near infrared color cuts as well as a visual inspection to the entire photometric data set. These color cuts are fairly standard, and I refer you to the paper to get more detail. And we get something on the order of about 120 candidates in total between redshifts 8 to 10. In total, it's 99 candidates at redshift 8, 14 at redshift 9, and 17 at redshift 10. These are dropout selected only. So we go one step further to try and pinpoint their redshifts through precise photometric redshift fitting with EASY. We also use the simulated prior for this, and this reduces the sample down to about 49 galaxies. And over here on the left, you can see the distribution of their photometric redshifts, and on the right, you can see the distribution of their H-band magnitudes. And because we allow a large parameter space for easy to simulate the Lyman break, it does mean that redward of about 1.6 microns, the SED is completely unconstrained. And so we go one step further to try and simulate realistic star formation histories with the SED-fitting code bagpipes. And this is just one illustration of what one of our sources looks like, where you can see the photometric data sets, including the IRAC bands and the best fit SED with which we try to measure the galaxy properties. So I've got to speed through, I think, but over 44 unique fields, we see 38 redshift 8 galaxies, 7 redshift 9, and 4 redshift 10 and above galaxies. And these are just examples of the postage stamps that you can see, as well as the SED fits. So now with our sample in mind, we go ahead to try and characterize their rest frame UV properties. On the left here, you can see the absolute magnitude and UV continuum slope as well with redshift. We don't find any significant trend between these, but we do compare to other sources in the literature. And we also look at the galaxy sizes, both at the bright end. This is the plot on the bottom right that you can see. On the y-axis is the galaxy size in log units. On the bottom is MeV and redshift. And we compare this to data that have been accumulated over wide fields as well as lensing clusters, such as the frontier fields. And you can clearly see the size magnitude relation at redshift greater than 6, where massive galaxies have sizes close to roughly 1 kiloparsec, and less massive galaxies, sub-kiloparsec sizes. Because we have Spitzer, we also go ahead and look at the rest frame optical galaxy properties. This is what you can see in this plot here. There are 6 different ones: stellar masses, specific star formation rates, stellar ages, ionization parameters, metallicities, and dust contents. And over here on the right, I'm showing you roughly the range that we probe. These are all considered so-called normal ranges of representative galaxies at redshift greater than 8. We also make use of the unique pure parallel nature of our data set, which means that cosmic variance effects are minimized because all of these sightlines are independent. And so we try and perform an interesting little test. When you look at the cosmic star formation rate density, typically this is derived using a luminosity function and converting that luminosity function to a star formation rate density using an assumed conversion factor. However, this conversion factor has not necessarily been tested and has been calibrated at lower redshift. And so what we do this time is we use detailed simulations of completeness to estimate the effective volume of our sources, as well as the star formation rates that we estimated with bagpipes to try and derive the star formation rate density of our sources in 3 different magnitude bins and 3 different redshifts. And we compare this to values derived with luminosity functions. In general, we find these are consistent. I'm happy to talk about them more, but we find the differences between luminosity function derived values and our ones are no larger than luminosity function differences between the luminosity functions themselves. And so this conversion factor does not appear to be a sticking point, let's say, for the most luminous galaxies. And discussions about the luminosity function constraints and densities of these galaxies is going to be presented in a forthcoming paper, Leto Chawalit et al., 2021, so keep an eye out for that paper. I'm running out of time, so I'm going to fly through this a little bit, but what about representative follow-up with JWST? NearCam is already going to go a long way to improving galaxy constraints, just with medium band, for instance, which you can see here on the plot on the left. These are wideband filters at the bottom with galaxy SEDs, and medium bands at the top, which better straddle galaxy SED properties such as nebular line emissions or continuum. And this can improve stellar age and stellar mass estimates by roughly up to 0.5 dex or so already. However, the power of JWST really is going to be in its near-infrared spectroscopy. And I was very pleased to wake up one morning to find out that my Cycle 1 proposal had been accepted to study 10 of these redshift 8 to 9 Super-BoRG galaxies with near-spec prism. We have 25.1 hours. This is going to be with near-spec fixed slit and MOS. And so we're going to be able to observe the full rest frame UV and also the majority of the rest frame optical spectrum at greater than 5 sigma in only 30 minutes to an hour. So this is going to be great because we can infer then the intrinsic properties of the galaxies and get their redshifts without being dependent on Lyman alpha. But because we get the Lyman alpha region as well, we cover the full rest frame UV spectrum, we'll also be able to link these intrinsic properties to the opacity of the IGM. And I refer to other talks that have been given before for comparison. And I think I'm running out of time, so I'm going to leave my summary and conclusions over here, that we conduct one of the largest searches for redshift greater than 8 galaxies with HST, finding nearly 50 candidates between redshifts 8 to 12. And we use this large sample to derive galaxy properties and test assumptions prior to observing some of these with JWST Cycle 1 observations. And so I leave it there. Thank you for your time.
Thank you very much, Guido. So there's some questions coming in.
Okay, so the first question from the Chana, very quick. So how do you calculate your UV slopes?
So the UV slopes are derived directly from the best fit SED with bagpipes. The idea was because we probe various redshifts, we wanted to be able to consistently compare the UV slopes. This is not possible with the photometry alone, given that at redshift sort of 10 and above, you maybe have a single point, whilst at redshift 8, you might have several detections of the continuum slope. So this is derived directly from the SED, and the same for the absolute magnitudes.
Okay, I think we have time for just one more question, but there's more questions in the Slack, Guido, that you can answer afterwards. But so I'm going to ask this question from Rebecca Bowler, who asks, how do the number densities of your brightest redshift greater than 8 sources compare to ground-based searches over several square degrees, e.g. UltraVista?
I haven't, so that's going to be compared by Nietzsche's paper. However, there are significant differences as well, but this is somewhat to be expected. Ground-based data are typically much shallower than the data we use by up to 1 to 2.5 magnitudes or so. And whilst the area afforded by the ground-based data might be significantly larger, these are also likely to be plagued by cosmic variance effects, given that these are just single pointing areas, which is not the case for our data set and is really the strength of the Super-BoRG data set, that 316 independent sightlines mean we can minimize cosmic variance effects. And so I would argue that the ground-based data are more likely to select sort of the extreme end of the bright end of the luminosity function, but we need to be careful in comparing data sets because they need to be first uniformly matched in depth and area.
Okay, thank you. So yeah, there's more questions
Thanks.
in the stack if you're able to answer
right,
those. Thanks.
I'll have
very
a
much
cup of
for your
coffee
thought.
and
Yeah.
cup of coffee, and then I'll answer them.
You
Thanks.
take your time.
Yeah,
All right.